According to Roots law, the vapor pressure of the solute containing solution is equals to mole fraction of solvent times the vapor pressure of pure solvent. So you will have this equation whereby partial pressure of A is equals to a mole fraction of solvent A times the vapor pressure of pure solvent A. Only the solvent A contributes to the vapor pressure of the solution. In order to calculate the partial pressure of A, we need to know the mole fraction. So what is mole fraction? So mole fraction of component is the number of mole of component divided by total number of mole of components. So let's say now we have in closed system we have component A, component B. So the mole fraction of A is equals to the number of mole of A component divided with total number of mole of components, which is N total. So N total is equals to the number of mole of A plus the number of mole of B. If let's say in the system we have component C and component D, so the N total will be number of mole of A plus number of mole of B plus number of mole of C plus number of mole of D. Addition of a non-volatile solute to a solution lowers the vapor pressure of the solution. The effect is simply due to fewer solvent molecules at the solution surface. This will decrease the mole fraction of solvent and will make the molecule less evaporated. The solute molecules occupy some of the spaces that will normally be occupied by solvent. Vapor pressure lowering also can be used to determine molar mass of solutes, which depend on the mole of solute. From the diagram, we can see the vapor pressure of the pure solvent, which is 3 atm, for example. When there are addition of non-volatile solute, which is the yellow color, it will lower the vapor pressure up to 2 atm. The presence of non-volatile solutes means that fewer solvent particles are at the solution surface, so less solvent can be evaporated. The diagram shows how a phase diagram is affected by dissolving a solute in a solvent. We understand that when solute dissolve in solvent, a solution will form. In the phase diagram, the black curve represents pure liquids and the blue curve represents the solution. You can see here there will be a triple point of solvent and there will be triple point of solution. We also can notice that in this phase diagram there are differences in freezing point and boiling point. For the freezing point of a solution, it is lower compared to freezing point of solvent. And also for the boiling point, the boiling point of solution is higher compared to boiling point of solvent. So this pressure we take at 1 atm. So there will be a difference in freezing temperature and also difference in boiling boiling point temperature. In vapor pressure lowering, according to Roots law, sum of mole fraction of solute and solvent is 1. So we can have mole fraction of A times mole fraction of B is equals to 1. If the solution contains only one solute, we can rearrange this equation. We can have mole fraction of A is equals to 1 minus mole fraction of B. The mole fraction of B here is a mole fraction of solute. So by substituting this equation into uh, the partial pressure equation, we can have partial pressure of A is equals to 1 minus mole fraction of solute times vapor pressure of pure solvent. So from here, you can do mathematics and you will have the final equation. The difference in pressure is equals to mole fraction of solutes times vapor pressure of pure solvent. There are few examples that involve calculation of vapor pressure lowering. Please help yourself to understand each of the question. If you have any problem, please ask me during our online class.